So hello everyone, this is the advanced section on quantum computing for the mini course on computation. And today we are going to have our teaching staff, Sowmya, talking about the basic and some future direction. Yeah, so Sowmya, maybe you can first briefly introduce yourself and then start the talk.
Hi everyone, I'm Sowmya. I'm one of the teaching fellows for this course. I recently graduated with a bachelor's degree in nanotechnology from SRM Institute of Science and Technology in India. And I'm working as a research assistant in my home institute. And today I'm excited to give this lecture on basics of quantum computing and some really interesting future directions of this field. So let's get started. So what exactly is a quantum computer? A quantum computer makes use of properties of quantum mechanics such as superposition, entanglement, to process information. We all know that classical computers store and process information using binary bits, which can take on binary values such as 0 or 1. Whereas a quantum computer stores and processes the
Oops, Sowmya? Sowmya, oops. Oh. Oh, Sowmya, I think we lost you.
Yeah, I'm really sorry. Yeah.
No worries at all. Take your time.
Okay.
Also, people are saying that your sound is a little bit low. Maybe you can increase the volume of your mic if it's possible.
Yeah, am I audible right now?
Slightly better. Yeah.
Okay. So I'll start once again. So quantum computers use the properties of quantum mechanics such as superposition and entanglement to process information. We know that classical computers that we use today use binary bits to process and store information, which the binary bits can only take on binary values such as 1 or 0, whereas a quantum computer stores and processes the information using qubits or quantum bits. So what is this quantum bit or a qubit? So like a classical bit, a qubit is a two-level system that exists in a state 0 or 1, or unlike its classical counterpart, a qubit can exist in both states simultaneously. We can also build a quantum computer with qubits, which is a three-level quantum system that can exist in state 0, 1, or 2, or a superposition of these states simultaneously. Say we have a qubit system with 100 qubits. The system will be existing in a superposition state of 2 power 100 states at the same time. Whereas a qubit system with 100 qubits, then the system can be in a superposition of 3 power 100 states at the same time. If we have a qubit system with, say, 500 qubits, then the system would be in a superposition of 2 power 500 states at the same time. This is greater than the number of atoms in the entire universe. There are several physical implementation of qubits, including photons, electrons, nucleus, ions, even superconducting transport qubits, etc. So let's talk about those weird properties of quantum mechanics which started all of this. So let's start with superposition. The definition of superposition is that a qubit can exist in a linear combination of two states, 0 and 1 at the same time. This ability of a qubit to exist simultaneously in multiple states is called as superposition. Because of this unique and weird property, a quantum computer with n qubits can exist in a superposition of 2 power n states. This is a mathematical equation which represents the superposition of a qubit. The alpha and beta are complex numbers which are known as amplitudes. When the qubit is in a superposition of states 0 and 1, when this qubit is measured, we'll get the state 0 with a probability of alpha square, and we'll be able to measure state 1 from the measurement with probability of beta square. There's an interesting interpretation of I know when I first read this topic, I was very confused myself. There's a really interesting interpretation known as many worlds interpretation, where it says that when the qubit, there exists two parallel worlds or multiple parallel worlds. In one parallel world, When we measured the qubit, we got state 0, whereas in another simultaneously parallel world, when we measured the qubit, we got state 1. So it's a very interesting interpretation, and it tells us that there's no collapse of the wave function, and information isn't lost. So if anyone interested, I'll link more information in the Discord about this. So the next topic is entanglement. A pair of qubits are said to be entanglement when the state of one qubit cannot be independently described from the state of the other qubit, which means both the qubits exist in a single quantum state. So let us take two qubit system with the first qubit in state 0 and the second qubit is in a superposition of state 0 and 1. It's denoted by plus state. So when you apply C0 gate to a system, C0 is a quantum gate, which I'll explain later on. So when you apply C0 gate to the system, you get an entangled state. So when you measure the qubit, the state of the first qubit, if you get 0, you immediately know that the state of the second qubit would be 0. Vice versa, if you measure the state of the first qubit and it shows that it's state 1, then you immediately will know that the state of the second qubit is 1. So quantum interference. So when two or more waves superpose with each other, it can result in addition of amplitudes of individual waves, producing a constructive interference. Or they can altogether cancel each other out, producing a destructive interference. This phenomena is known as wave interference, and quantum interference in quantum computing can help us control the probability of quantum system of qubits, thus collapsing them in particular desired measurement. It means that quantum interference can help us cancel out the wrong state and amplify the probability of getting the desired state. This equation is an example of quantum interference where we have a qubit which is in plus state and a second qubit which is in minus state. You can see from the equation that the state 0 of the plus state which of the first qubit will constructively interference with the state 0 of the second qubit which is in minus state, whereas state 1 of the first qubit will destructively interference with the state 1 of the second qubit, thus will get state 0. um, Quantum decoherence. So quantum computers are very vulnerable to errors that arise from decoherence. Quantum decoherence is the loss of quantum coherence. This occurs when the environment interacts with the qubits, resulting in uncontrollable change in quantum states, causes the loss of information which is stored by qubits. So decoherence is caused by radiation, environmental interactions, magnetic fields, cosmic rays, and even temperature. This is an example of quantum decoherence where, say, there's a qubit with heads or tails. There's a coin which is in heads or tails, and it interacts with the environment, and it splits into heads or tails, any one of the state. So thanks to this bizarre quantum properties, quantum computers can perform more powerful in solving certain problems that conventional classical computers cannot. So let's talk about blot sphere. A blot sphere is a sphere which provides visualization of the state of a single qubit. It is a state space consisting of all possible points.
Sowmya, sorry to interrupt, but
Yeah,
there's a question in the chat. Yeah, and maybe it would be better to answer that before you introduce blocks. Yeah, so
okay.
yeah. Can you read the chat or should I read out for you?
Uh, okay, so how do you minimize the amount of decoherence, right? Okay. There's ton of there's a I guess a framework called as quantum error correction. There's ton of literature on it where various methods are used so that they can minimize the effect of environment on our qubits. Um, yeah. And also it's important that we protect our qubits from interacting with the environment. So you can do it physically or you can make some changes in the quantum circuit. Can I move on? Okay, so let's start with block sphere. So a block sphere is a sphere which provides visualization of the state of a single qubit. So it is a state space that consists of all possible points to which a state vector can point. Each point on our box sphere represents a quantum state. So previously I was talking about plus states. So this plus states is denoted by this equation, where it's a superposition of zero state and state one. Minus state is also a superposition of state zero and state one. I plus is also another superposition of state zero and one. So let's dive deeper into quantum circuit. A quantum circuit contains a sequence of quantum gates acting on quantum bits or qubits to manipulate quantum information. There are two types of gates. There's reversible gates and non-reversible gates. Gates which preserve all information. That means given the output of the gate, we can determine what the inputs of the gates are. And non-reversible gates are the gates that lose some information. So given the output of the gate, we cannot determine what the inputs are. An example of a reversible gate would be a NOT gate, whereas an example of a non-reversible gate would be a measurement gate. So when you measure a qubit which was in superposition, the wave function of the system collapses in either state 0 or state 1. So quantum gates are the operators that evolve the state of the qubits, and they're unitary and therefore reversible. A measurement quantity or observable is a Hermitian operator, so therefore the measurement in a quantum computer outputs real values from the system. So one of the important single qubit gates in quantum computing are polygates, which are denoted by X, Y, Z. Their matrix form is known as polymatrices, and they're both Hermitian and unitary. The X gate, which is known as which is a well-known gate, is known as bit flip gate or sigma X. It acts similar to a classical NOT gate. So when you apply X gate to a quantum state, which was, for example, we are applying X gate to state 0, it flips the state of the qubit to state 1, vice versa. This is a matrix representation of the X gate, and this this sphere is known as block sphere. So previously the state vector was pointing towards the state 0, but as soon as you apply the X gate to the qubit, it flips the state of the qubit to state 1. So Y gate is also known as bit and phase flip gate because it flips both the bits and relative phase. So when you apply Y gate to state 0, you get I state 1. Here I represents the global phase. It does not have any physical significance, but it represents that how the Y gate flips both the relative phase as well as the bits. And this is a matrix representation of Y gate. Then we have Z gate, which is known as phase flip gate or sigma Z. It flips the state of the qubit by 180 degrees. There's no classical analog for this gate. The Z gate, when it acts on plus state, it flips it to minus state. Similarly, if it acts on state I plus, it flips it to I minus. And this is the matrix representation of the Z gate. So say our qubit is in state plus. That means it's halfway between state 0 and state 1. It's in a superposition of both the states. So when you apply a Z gate to this qubit, it flips it to minus state. Next, we have phase gate. So phase gate is a parameterized gate. So it performs a rotation of an angle around the z-axis. So if this angle is equal to pi by 2, so you call it as S gate. This is the matrix representation. So say the angle is equal to pi by 2. So when you and our qubit is in the plus state, so it's halfway between states 0 and state 1. So when you apply the SK to our qubit, it flips it to it does a quarter turn around the Bloch sphere, so it flips it to I plus state. Now let's talk about T gate. So it's a phase gate with theta is equal to pi by 4, and it performs a rotation of pi by 4 around the z-axis. So this is a matrix form. So you have a qubit which is in plus state, so it's pointing along the x-axis. So you apply the phase gate, T gate, and then it performs a rotation of pi by 4 around the z-axis. We have Hadamard gate, which takes the state of our qubit and puts it into a superposition of two states. So you have a qubit which is in state 0. So when you apply Hadamard gate to this qubit, it puts the state of the qubit into a superposition of state 0 and state 1, which is represented by plus state. Similarly, when you apply Hadamard gate to state 1, it puts the state vector of a qubit in along the state minus. And this is the matrix representation of the Hadamard gate. Multi-qubit gates. One example of multi-qubit gate is C0 gate. It's a conditional gate that performs edge gate on the second qubit, which is also known as target qubit, if the first qubit, also known as control qubit, is in state 1. So you have two qubits. The qubit 1 is in state 1, whereas qubit 2 is in state 0. So when you apply C0 gate to the C0 gate, then qubit 2 will flip to state 1 as well. So it will apply an X gate on qubit 2 if the state of the first qubit is in state 1. This is a matrix representation of C0. The swap gate swaps the states of two qubits. So if you apply swap gate to a state 1, 0, you get 0, 1. So for example, you have a qubit 1, which is in state 1, and you have a qubit 2, which is in state 0. So when you apply a swap gate, this qubit 1 flips to state 0, whereas the qubit 2 flips to state 1. So there's an exchange of states. So the Toffoli gate is a 3-qubit gate with 2 control qubits and 1 target qubit. It performs an X gate on the target qubit if only both the control qubits are in state 1. It's also known as control NOT gate. So when you have 3-qubit system with qubit 1 in state 1, qubit 2 in state 1, as well as, but qubit 3 is in state 0. So when you apply this gate, the qubit 3 will flip to state 1 because both the first and second qubits are in state 1. So let's talk about Solvay-Kittel theorem. So it says that
so maybe it's a good time to pause a little bit to make sure people understand the content gates you are talking about so far.
Oh yeah.
Oh, I mean, you can ask if people have any clarification questions.
Yeah. There are several gates. I've just introduced few of them. So yeah, there are several gates. I've just introduced some of the important gates.
Someone also asked about Hadamard gate. Maybe you can also read out the questions.
Yeah.
For your answer.
So why are we applying Hadamard gate to a state basis of 1 maps to a negative state? So yeah, so here so just to show that when you apply Hadamard gate to state 1, it flips it to the state negative state, which is just a superposition of state 0 and state 1. Yeah. So for a visual interpretation, so state negative would be pointing towards this axis, negative x. For example, so there's a qubit which is in state 1. So when you apply a Hadamard gate, it will flip to the state negative, which is halfway between state 0 and state 1. It's a superposition. The only difference is the relative between state plus state and minus state is the relative phase, which is between which is represented by the negative sign. So I'll get started with solver-to-tape theorem. So the theorem says that let G be an instruction set for SUD and let a desired accuracy of epsilon be greater than 0 be given. There exists a constant C such that for any U in SUD, there exists a finite sequence of S of gates from G of length order of log per C 1 by epsilon such that B of U comma S is less than epsilon. So this theorem just basically roughly states that all finite universal gate sets can simulate a given gate set to an arbitrary accuracy of epsilon. So we know that in classical computation, NAND gate alone is sufficient to construct any classical computation. And the definition of quantum gates is that quantum universal gates are that a set of universal quantum gates is any set of gates to which any operation possible on a quantum computer can be reduced. So there are two universal quantum gate sets. One includes C naught and gate P and phase gate. The other one includes Toffoli gate and Hadamard gate and phase gate. And using these gates in a quantum circuit, we can approximate any unitary operation in quantum computing. So let's talk about BQP. It's known as bounded error quantum polynomial time in computational complexity theory. It's a class of decision problems solvable by quantum computer in polynomial time with an error probability of at most 1/3 for all instances. It's a quantum analog to complexity class BPP. BQP is a class uh, that contains all decision problems with yes or no answer, and those that quantum computers can efficiently solve. Before we dive into future directions, I'm going to share how we can create quantum circuits using Qiskit, which is open source software development kit by IBM so that we can work with quantum computers. So, okay. So using Qiskit, we can create quantum circuits and quantum algorithms. So the most basic quantum circuit, which I've already created, which involves a measurement. So there's a quantum circuit with a qubit one qubit and a classical bit, and the quantum bit is measured onto the classical bit, and this is how it's represented on a Bloch sphere. By default, the qubit is always in state 0 initially. So when you apply an X gate to this qubit, it flips the state of the qubit to state 1. And this is a representation of Hadamard gate. Initially, it was in state 0. So when you apply a Hadamard gate to a state 0 qubit, it flips the state of the qubit to plus state, which is halfway between state 0 and state 1. And in case of Y gate, I've applied Hadamard gate, so the qubit is already in a superposition, so it's in place plus state. So when you apply a Y gate to a plus state qubit, it flips the qubit state of the qubit to minus state. In case of Z gate, so again, I've applied a Hadamard gate to the qubit, and then I've applied a Z gate to the qubit. Initially, the qubit was in plus state, so it was pointing along the x-axis. And after applying the Z gate, it flips the state of the qubit to minus state. And then we have S gate, which is just a phase gate with theta is equal to pi/2. Again, once again, I've applied HUD-MUD gate before the S gate. So initially, the state of the qubit was along x-axis. It was in plus state. So when I applied the S gate, it flips the it does a quad it flips the state of the qubit to plus I along the y-axis. Again, with the T gate, initially the qubit was pointing along the x-axis, and after applying the T gate, the qubit pointed. So it does a pi/4 rotation around the z-axis. So the C0 gate is represented by the symbol in Qiskit. So you have two qubits. I've taken two qubit circuit and two classical bits. So you have an X gate, which is performed on the first qubit, which is represented by Q0. And then I've applied a C0 gate with the first qubit as a control bit, qubit, and the second qubit as a target qubit. So initially, the qubit 1 was in state 1, qubit 0 was in state 1, and qubit 1 was in state 0. So after applying the C0 gate, the qubit 1 flips to state 1 because the qubit 0 is in state 1. So you have swap gate, which is represented by this symbol. I've applied a X gate on qubit 0, and then and the qubit 1 is in state 0, whereas qubit 0 is in state 1. So after applying the swap gate, it swaps the state vectors of both the qubits. So the qubit 0 flips to 0 state, whereas qubit 1 flips to state 1. The Toffoli gate is represented by this symbol. So I've applied an X gate to the state qubit 0, and I've applied another X gate to the qubit 1. And the qubit 0 and qubit 1 are control qubits, whereas qubit 2 is target qubit. So after applying the gates, the qubit 2 flips from state 0 to state 1 because both the control qubits are in state 1. So let's create an entanglement state. So it's very easy to create an cell state, which is known as entanglement state using Qiskit. So you apply HUD-MUD gate, which puts the state 0 in a superposition of 0 and 1 states. And then you apply a C0 gate with qubit 0 as a control qubit and qubit 1 as a target qubit. So after applying, you can measure we can measure that with you'll measure that with 52%. You'll be measuring state 0, 0 on qubits, and with 47%, you'll be measuring state 1, 1. And it's represented by block sphere, where if you measure the qubit 0, the state of the qubit 0, and if it shows it's pointing towards state 1, you immediately would know that the state of qubit 1 would be pointing towards state 1 as well. This is a very simple way to we can create quantum circuits using Qiskit. There's also another platform which I'll be sharing now.
Oh, by the way, Sowmya, someone is asking, we're going to make your slides and call the public after the talk.
I'm sorry, can you repeat the question?
Oh, I mean, people are asking, are you going to put your slides like in public and the code?
Yeah.
Okay, great, thank you.
This is known as IBM, I guess IBM Quantum Platform. I started learning about quantum computing through this platform, so I suggest everyone who's beginner, who's interested in learning about quantum computing, to start with this platform. It's very easy to learn. So there's a couple of gates here. You can just pull and drag and place it, and you can create your own quantum circuit. For example, here I've created an entanglement. So there's a qubit with 50% chance of it being in 0, 0 state and 1, 1 state, and it's represented by Q sphere. And yeah, if you want to, this gate is known as Hadamard gate, and there's a NOT gate as well. So you can, for example, you can perform. So yeah, you can drag, pull and drag any gates, and you can, yeah. So you have two qubits in state. There's one qubit where I've applied NOT gate, so it flips to state one. Whereas there's another qubit, qubit one, which is in state zero. Since I performed CNOT, the state of the qubit one will flip to state one as well. So the state of the system is 111. So coming back to our slides, so I'll talk more about future directions of quantum computing now. So one important application of quantum computing is quantum chemistry. So since nature surrounding us is intrinsically quantum, the classical machine learning has long been successful in solving classical problems. But as we know, the size of quantum systems such as molecules increases, the Hilbert space of the system also scales exponentially with the size. So therefore, modeling such problems or systems is classically infeasible. So since quantum computers make use of quantum mechanics properties, they can efficiently simulate such quantum systems. So simulating quantum systems using quantum computers will allow us to study in remarkable detail the interaction between atoms and molecules. And there's certain companies like Volkswagen and Daimler are using quantum computers to find new ways to improve the performance of electrical vehicle batteries by simulating the chemical composition of these batteries. I'll talk about a very important quantum classical, hybrid classical quantum algorithm, which is known as variational quantum eigensolver. This algorithm variationally determines the minimum eigenvalue of the Hamiltonian matrix. So it's widely used in quantum chemistry simulation. The Hermitian matrix minimum eigenvalue of the system is actually its ground state energy. So, and variational quantum eigensolver is based on variation principle, according to which the expectation value of the system's Hamiltonian is always greater than or equal to the system's ground state energy. And by using the trial wave functions, the Hamiltonian's expectation value can be calculated. Thus, we can determine the ground state energy of the system by simply varying the trial wave function until we get the minimum expectation value of the Hamiltonian. Thus, we obtain the system's ground state by through this equation where the wave function, which is parameterized, called as trial wave function. So when you I'll explain further through this. So for determining the molecular energy, ground state energy using VQE, so we first prepare the molecule's ansatz. Ansatz is basically a quantum circuit which helps us construct a trial wave function, which is represented here, a trial wave function. And
sorry, are you using your slides now?
yeah,
Now we are seeing still seeing the IBM simulator.
oh, sorry.
Yes.
I'm so sorry.
Mhm.
Oh, sorry. Is it clear? Is it visible now?
Yes, yes.
I'm really sorry. Yeah. Yeah. So I was talking about how VQE is like a hybrid classical quantum algorithm that variationally determines the minimum eigenvalue of a Hamiltonian matrix, and it's widely used in quantum chemistry simulation. And I've already defined the variation principle, and it's given by this equation where using trial wave function, we can find the minimum eigenvalue of the system. So this is a illustration to illustrate variation quantum eigensolver. So for determining the molecule's ground state energy using VQE, we first prepare the molecule's ansatz. So ansatz is a quantum circuit which prepares, which constructs the trial wave function of the system. And then here, the parameterized quantum circuit represents an ansatz. And then we compute the Hamiltonian's expectation value. After computing the expectation value, we feed it to the classical optimizer, where an optimization algorithm um, um, updates the updates new parameterized so that we can obtain minimum eigenvalues. So this process will be taking place until the minimum expectation value is obtained. So quantum circuit parameters are updated. Parameters of quantum circuit is updated by classical optimizer until we obtain a minimum expectation value. Another potential application of quantum computing is drug design and development. Quantum computers could help us design and develop new drugs. So pharmaceutical companies are leveraging them to analyze and compare compounds that could lead to new drugs. Designing and developing a drug is very expensive, very risky, and challenging and time consuming. Since quantum computers are efficient in simulating behavior of matter down to the molecular level, they can help us effectively understand drugs, discover new drugs, help us study their reactions on humans. Therefore, quantum computers can help us make this process less time consuming and inexpensive. This is an example of the process where of discovery and development, where we first target an identification. We identify a molecule which is targeted by a specific disease, and then demonstrate that this is druggable, and then we develop compound which can act on the target and optimize it for effectiveness and safety. And there's preclinical development. There's extensive tests in vivo for drug safety and side effects, and there's clinical trials on humans, which for monitoring the drug dosage, safety, etc. This illustration shows that flowchart shows that the average time that it takes for each process to take place through the drug discovery and development. So you have first drug discovery phase, where the average duration is 5 years. There's identification of diseases, and there's identification of drug of interest. And then you go on to preclinical trials, where there's various steps involved, and the duration of this phase is 1 to 3 years. And then you have clinical development, where again there's various phases involved, and the duration is about 2 to 10 years. So average is about 5 years. So, and then there's phase 4, where you monitor long lasting side effects, which again takes a lot of time. So it's clearly seen that the entire process of drug discovery and development is very time consuming, and it takes a lot of time, as well as it's very expensive. So we're hoping that quantum computers can shorten this time and make it inexpensive. Another potential application of quantum computing is in solving complex types of optimization problems. For instance, we know a well-known problem known as traveling salesman problem, which aims to determine the shortest possible route between multiple cities and return to the starting point while visiting each city at once. The traveling salesman problem is complex for a classical computer to solve. There's one research group which took, I guess, 10 months to solve 25K city problem, whereas they took 1.5 years to solve 49K city problem. And using superposition, quantum computers can represent all possible solutions. Thus, the use of interference will help us obtain low cost and high value solutions. This illustration shows that adding more stops takes longer and longer to figure it out. So yeah, quantum computer could help us solve optimization problems. Another application of quantum computing is high energy physics. Inside a particle accelerator, the collision of two heavy ions produce assortment of fundamental particles, and they produce vast amount of data as well. And simulating even a tiny bit of this process, which takes place inside a particle accelerator with a classical computer, would take longer than the age of the universe. Since nature is fundamentally quantum mechanical, quantum effects are hard to model on non-quantum devices, and quantum classical machine learning techniques are used to analyze raw data captured by particle detectors right now. Since qubits, since they obey the laws of quantum mechanics such as superposition, entanglement, they can hold more information than classical bits. Therefore, quantum computers can visualize and handle more dimensions than a classical computer. The quantum algorithms using quantum kernel method can enhance the feature space and thus see patterns in vast data sets and carry out classical tasks, classification tasks, in contrast to a classical computer, which would only see a random noise in that area. This image shows that shows a collision between two heavy ions in a particle accelerator. You can clearly see there's assortment of fundamental particles which are produced, and the red blocks which are shown in the image represent the detectors. And it's clearly seen that there's so much data which is produced through these events. And Large Hadron Collider is currently being upgraded, and the next iteration of the system would come online in 2027. And they predict that there'll be more collisions, like 10 times more collisions than the current machine. So it won't be long before the classical computers would be unable to handle this data. And there's a team at IBM which is creating a quantum algorithm known as quantum support vector machine. They're using this to identify collisions that produce Higgs bosons. And the algorithm was trained with a test data set based on information generated by one of the LHC's detectors, and was run on both quantum simulators as well as physical quantum hardware. And in both cases, the results were promising. It's a really interesting field. There's a ton of applications of quantum computing, not just in these four applications. I'll link the papers in the Discord if anyone is interested to check them out. Another important topic in quantum computing is quantum algorithms. An algorithm is a step-by-step procedure to perform a calculation or a sequence of instructions to solve a problem, where each step can be performed on a computer. Therefore, an algorithm is quantum algorithm when it is performed on a quantum computer. One such algorithm is Grover's algorithm. In mathematical terms, Grover's algorithm solves the problem of unstructured search. It is a quantum algorithm for finding input value x0 of an oracle function f of x with an x0 is equal to 1, and f of x is equal to 0 for all other values of x. The strength of an algorithm is that when the oracle function has n possible input values, the algorithm only requires order of square root of n evaluations of the oracle, while the best classic algorithm needs order of n evaluation. So an example of this would be a problem of finding a specific card in a shuffle deck of n cards. So classically, you have to search each and every card one by one to find that specific card. So you would need n steps to find it. Whereas Grover's algorithm requires only order of square root of n evaluations of the oracle. Are there any questions? Yeah. Yeah, it's considered to be faster than a classical one. The quantum computer search. The question was that how does a quantum computer search is faster than a classical one? Here in the example, we need to find a specific card in a shuffle deck of cards and cards. So in classical case, you have to go one by one. So you would take like n steps to find it. Say, but then in case of a quantum algorithm known as Grover's algorithm, you would only require order of square root of n evaluation steps to find that specific card. Um, These are some of the reference materials that I've collected regarding the applications of quantum computer. I will link them in the Discord if anyone interested to learn more about these applications.
So maybe let's thank Sowmya for the great introduction to the basic of quantum computing. Yes. Yeah, and since we still have like 10-30 minutes before the next section, maybe people feel free to ask any questions. Yeah. Yeah, I actually have some questions, but I also encourage people to ask first. Yeah, otherwise I'll occupy too much time. So.
I think I could ask a question. So you mentioned that these quantum algorithms could be a bit better at solving optimization problems than classical computers. And you mentioned this traveling salesman problem as an example, but I just want to check that probably, I mean, this same way of thinking probably also works for other NP problems, because so because Chi-Ning mentioned this, that basically the idea is that you somehow keep track of these some weighted combination of path integrals, or maybe these paths in this traveling salesman problem, and it seems like the same way of thinking also works for other NP problems. So it's just so I just wanted to check that it indeed is the case that this traveling salesman problem is not really an exception, but maybe these quantum algorithms could also be more useful at solving other optimization problems. I mean, with real life or real world instances, if that makes sense.
Yeah, I agree. Actually, this is one example that I used to explain that there is a certain application of quantum computing in solving optimization problems, but there's ton of research going in this field. I think I link more materials if when I find them related to how quantum computing is used in solving optimization problems.
Okay, sorry, I was searching for some references for the chat, but I do have some questions. Yeah, so for the drug analysis application you were mentioning, yeah, since there are many different stages, my guess is that probably quantum will just plays a role in some of them. Like what's the main part? My guess would be maybe discovery, or I don't know, because that part, even you make mistake, it doesn't matter that much. And is that the case? And also I'm curious, like what's the what in practice people like already have, like in the applications of quantum in the drug analysis. Like, do people really started to use it? Or?
Yeah, they've used quantum machine learning algorithms in discovering drugs. I mean, majorly for now, I think it's being used in the drug discovery phase, where you identify, you study the interaction of the disease molecule and the drug of interest, or you even study the drug molecule or the material and the properties of the various drugs. So I think right now the research is mainly focused in drug discovery. But yeah, I've seen certain research going using quantum machine learning algorithms in drug discovery. Yeah.
But do you have the intuition of why quantum can be helpful here? Like, is this similar to like the optimization application where here you can, or like similar to intuition global search, like you roughly know what you can easily verify whether a given drug is good enough or not. Yeah, so that you can use like a superposition of lots of possibility to search. Is that roughly the intuition or?
I think that's one of the intuition also that since these molecules are in quantum in nature, so I think using a quantum computer to study these properties, which are quantum in nature, is makes more sense than using a non-quantum device to study a quantum system. So I think that was the basic idea. But then, as there's so much different research which is going in this field, yeah. Another one would be using quantum properties of qubits to, yeah, to find the most optimal drug material which is most suitable in fighting that disease.
I see, I see. This makes sense. Yeah. Oh, but maybe one more question on this. Like, do you know how many qubits roughly is needed to, I mean, to simulate a meaningful drug? Like, is it of the order of like a 10, like a 50, or it's like hundreds?
I mean, it depends upon the molecule. So it scales with the size of the system. So the number of qubits that you would require would scale with the system. So if it's a very small molecule, you would require less than 10 qubits. But if it's increasing, then you would require, I guess, 100 qubits or more. But currently, I think we have access to 100 qubits or in that range. But this field will grow with the quantum hardware that we have access right now. So as the quantum hardware systems get better and there's more access to the qubits, I think this field will be benefited with it.
I see. So let me make sure I understand. So you are saying the more the better, and even just tens or like thousands can already be a little bit useful.
Yeah, the more the better.
Mm-hmm. But 10 qubits already can give you something.
Yeah, you can simulate, I guess, small molecules with it.
Mm-hmm.
So there was this, I recently participated in an IBM quantum challenge where we were able to simulate the ground state energy of a drug molecule. I don't know the interaction of a drug molecule with HIV molecule. So we've used, I guess, around 10 qubits, but yeah.
Mm-hmm. I see, I see. Great. Yeah, thank you.
I have a question, Sowmya. So you talked about this traveling salesman problem, right?
Yeah.
So did you mean to say that like using a superposition on this quantum computer, did you mean to say that we can actually solve this traveling salesman problem in quantum polynomial time? Because like if that is the case, then we have effectively shown that NP is contained in BQP, but that is not yet known, right?
I think, yeah, I guess we can solve this, the traveling salesman problem in polynomial, quantum polynomial time. But yeah, I'm not sure about this. I'll look into it actually.
I think I actually explained a little bit in the chat. I think the problem here is like there are actually multiple problems. Yeah, the first problem is like usually it's like just people just empirically show you can solve certain real world instance rather than worst case TSP input. And second, usually they not really like give you optimal solution. It is just some solution quite good, but usually not the optimal one.
Yeah, right. So, okay, it is some like alpha approximation to the TSP solution and not the exact solution.
Yes. And furthermore, theoretically, I don't think people really can analyze this. Yeah, like yeah, this kind of stuff usually just heuristics. Yeah, like theoretically, it is really hard to prove something. Yeah,
yes.
Yeah. But there's some work maybe focus not on the polynomial time regime, but in the setting where people call it local algorithm. Yeah, and this is related to the QA/OA things I put in the chat. So there are slightly more theoretical guarantee there and also some empirical evidence, but it's still like in development. So if you are interested, maybe you can take a look. there's another questions in the chat. Hmm.
Yeah, yeah, we can store classical data in quantum systems, but yeah, we cannot completely encapsulate the quantum data in classical systems.
Okay, so maybe let's thank Sowmya again, and we can have a break before Vantika section. Yeah.